In today's talk, I will focus on fundamentals of sample preparation. I will discuss how to use the fundamentals to optimize extraction of both homogeneous and heterogeneous samples. The present situation in academia is such that we don't specifically cover fundamentals of sample preparation as a separate topic. So I have been doing in my lab trying to develop those fundamentals. So rather than using trial and error approach in optimization of sample preparations, I was using more scientific principles, more rational scientific principles to accomplish the goal. What I discovered in the process is that I can develop very interesting experiments and projects for the students and at the same time obtain more information about the investigative system. Fundamentals of thermodynamics of extraction are well known from curriculum of physical chemistry, so everybody's familiar with the distribution constant. However, it's less familiar when you talk about kinetics of extraction. When I look at the different extraction methods, what I discovered that you can develop it, divide it into three groups: flow-through techniques, batch techniques, steady-state techniques. Flow-through techniques can be modeled reasonably well by chromatographic principle for low-resolution chromatography, especially frontal chromatography, but what I will talk about today is about batch extraction techniques. So example of the batch extraction techniques is the extraction of water. So you can perform it in an exhaustive way using a copious amount of organic solvent, like 40 milliliters of organic solvent, or you can do it by, for example, SPME, where you have only 1 microliter of the extraction phase. What you discover, though, that amount of analytes injected onto the analytical instrument is identical. And the reason for it is high enrichment factor, because the concentrations of analytes in the extraction phase in SPME are much higher because you don't change the concentration in water by extracting 0.1% of analytes from water, while you substantially deplete the concentration in water because you reach almost exhaustive extraction. So the concentration in solvent is much less. In addition, as you can see, it's very easy to couple the sample to the analytical instrument with SPME compared to liquid-liquid extraction, which provides automations and also facilitates on-site analysis because you are independent on the water sample volume. So you can see that there's no volume of water in this equation when you have a negligible depletion conditions. Of course, everybody is concerned about recoveries because recovery is the guiding principle in a lot of extraction. But what I discovered that in SPME, we have 100% relative recoveries. This means if you match the matrix by using matrix match calibration, we actually find the same amount of analytes extracted in matched matrix than in real sample, which allows us 100% relative recovery, still keeping high enrichment factor, high sensitivity. The way to increase the sensitivity in SPME is to either change the K, selectivity of the extraction phase, or you can change the volume of the extraction phase. When you want to change the volume of the extraction phase, you need to be careful to not increase the time of extraction. So you can consider various different geometries in SPME. This is one of the advantages of SPME, that you can coat any different surfaces with extraction phase. So for example, if you go from fiber geometry to thin film disk geometry, you keep the same surface to volume ratio. This means you keep high contact between the extraction phase and the sample matrix, so you don't decrease the extraction. And practically, we have accomplished that by designing the thin film microextraction, which is basically impregnated carbon mesh with the sorbent rather than coated fiber. And as you can see, we have much higher surface area, but also much higher volume of the sorbent, which allows us to reach the equilibrium at the similar, as I will show you in a moment. Of course, the complication is that you need to have a special interface to analytical instrument. So you can use a line exchange system, for example, Gerster line exchange system, of, for example, Thorium, Pekin-Elmer on-site analysis system, or Marcus thermodesorption system. And as I was mentioning, if you look at the profile kinetics of SPM extraction versus thin film, they're basically identical. The equilibration is about the same, but the amount extracted is about 50 times higher, which corresponds to the phase ratio of the extraction phase. Now, if you compare, for example, thin film to the twister, which based on the increasing the thickness of the extraction phase, you of course see substantially faster. The thin film is substantially faster. And also with twister, there is a problem because you rotate and you speed up, move the water. So the relative velocity of the water in twister is lower compared to thin film, where you use, for example, vortex agitations. So that creates a higher boundary layer against causing the longer equilibration times. Practically, we try to use it to develop effective way of water analysis. I'm very concerned about current state of art of doing water analysis, which is based on liquid extraction. So you sample the water. Typically, you sample the water in 1 liter bottle, then you do liquid extraction in the laboratory. You can do subset of analysis using SPME, which has been tried a long time ago. However, it was found that for hydrophobic analytes, you're losing some of the analytes on the surface of glass. So liquid extraction data are not the same as SPME data or SPE data, to the, similarly. But what you can do here is to place the insert in the cap of the bottle and hang the thin film in the bottle. So as soon as you sample the water, you immediately start performing extraction to avoid. And look how the results look like. So if you have a standard water analysis system performed by the commercial lab, Maxam Analytics, versus the thin film microextraction in bottle approach, as you can see, it's as what we said, it's about close to 50 times lower method limits of quantification. So this is very good opportunity to green up the way of water analysis, which is done in larger amounts. Now, when you analyze heterogeneous samples, especially solids, you need to also consider some other processes, like, for example, release of adsorbed analytes present in the sample matrix before it can be mass transport through the sample matrix, partition into the extraction phase, mass transfer of in the extraction phase, and removal of the extraction phase. So the processes in a heterogeneous matrix are much more complex. Here's an example of doing heterogeneous matrices. So let's say a soil sample, and you have look at the particle in the soil sample. We have a solid silicate, so this is this white in the center, one part in the center. Green is humic material. Analytes are adsorbed in a pore, deep in the pore in a silicate. And in order to remove it and extract it, you need to dissociate it from the surface. You have a dissociation rate constant, diffusion coefficient in the humic material, then diffusion out of the pore, partitioning and diffusion out of the pore. And if you look carefully about these fundamentals, which I developed in this paper, you'll notice that the temperature plays an important role. Then increasing the temperature allows us to increase the rate of extraction. So that's why we propose eventually suprafluid extraction based on high temperatures, which eventually was used also as a high temperature extraction method. You can also use those principles in designing high temperature desorption in the SPME format, but here you have a vial instead of water. You have a solid sample. You heat up the solid sample, you release the analytes into the headspace, and you pick up by the fiber. But to keep the fiber cool, you have a special mechanism to cool it using CO2. And by doing those, you accelerate mass transfer rate because diffusion coefficient, dissociation rate constant are faster at the high temperature. You you release analytes into head space because Henry constants are faster. And in addition, you have also fundamental enhancement distribution constant given by this equation. So it is due to the fact that there's a temperature difference between the sample, which is high temperature, and the fiber, which is the lower temperature, that allows you to have much higher K value. So if you go have example, so here a commercial fiber, so DVB, carboxyl, PDMS, commonly called sandwich fiber. If you increase the temperature, so this is when you increase the temperature from 100 degrees to 200 degrees, you can see loss in sensitivity for more volatile components, some increase for less volatile components, but in cold fiber SPME, even with weak sorbent like a PDMS, you will see extract much more, and there is no loss in sensitivity for naphthalene because you keep the fiber at the constant temperature despite of increasing the vial temperature. So this is called cold fiber SPME approach. And we recently did validation of this approach using versus certified value based on soxhlet extraction. As you can see, there is a good agreement between cold fiber SPME versus the certified values. The pressure balance means that I reduce the pressure at the beginning to not produce the additional pressure by heating the vial, but the results are very similar. Now, when we are talking about complex samples of biological nature, you usually have some binding matrix, could be proteins, tissue components which bind the analytes. You have some free concentration of analytes or metabolites, whatever, in equilibrium with the bound form. And so when you can do extraction either via headspace, but here you need to make sure the Henry constant is high because you're talking about the multi-phase equilibrium, which also involves a partition into headspace. Or you can do direct extraction from the aqueous phase or directly from the tissue. To do directly extraction from the tissue, which of course has benefit because we not relying on the Henry constant, we can extract all the analytes for which extraction phase has some affinity. What we need to do is to employ the protection layer. So it means we overcoat the extraction phase with the additional coating or protection layer. And this could be the PDMS or PEN. What we are doing here, we actually paint the substrate, which could be fiber or blade or whatever we do, with the composition of the sorbent, which is those pink particles, and the binder, yellow particles. And the binder has this matrix compatible properties. So when you add the sample, like for example, here it could be blood, the metabolites in blood or some drugs in the blood can be extracted via the protection layer into the sorbent. Then when you exchange it for desorption solvent, you can dissolve it and then analyze. What we found in this particular experiment that there is a so-called balanced coverage obtained. That means we both extract polar and non-polar analytes. This is due to the fact that although hydrophobic analytes has higher affinity towards the fiber, they also have higher affinity towards the matrix component. So there is this competition of the matrix component. So for hydrophilic analytes, we don't have a competition, but have a lower K value. For hydrophobic, you have a competition and you have a higher K value. So here's the example of how does this work. So again, you have this multi-phase equilibrium as I showed you here, defined by different rate constants and distribution constant. And you can see for polar analytes like a morphine, there is not much difference between its amount extracted in plasma and in PBS because the binding to the plasma components are low. However, for steroid, the situation is different. You have almost exhaustive extraction for in PBS, but only a few % extraction from plasma. So that's a balanced coverage, allows us to extract both hydrophilic and hydrophobic analytes about the same amount within the range compatible with the coating property. Now, the same applies when you do tissue analysis, and in fact, you see some very interesting phenomena here. So basically, when you extract the static extraction from protein-free tissue, so like a PBS gel, you have very long equilibration time, which is the extraction profiles extend for large distances. When you apply to tissue here, you see extraction time is only 20 minutes. So this is like a day extraction equilibration time. This is 20 minutes. And the reason for it is because there's analytes available close to the fiber, which are bound to the matrix. As you can see, the amount extracted, of course, it's much less in tissue, less than 10%, 7% or so. But so most of the analytes are in tissue components which are located in the vicinity of the fiber, which are then available for fiber to extract. So obviously I was talking about multi-phase equilibrium, so you don't need to only measure the concentration of the component in the matrix, but also measure the affinity, this distribution constant between the free concentration and the sample component. So the typical way of doing that in the pharmaceutical industry is measuring the plasma binding constants for different drugs, and this is possible with SPME. This is, you can see here the recent introduction from Supelco, where you can do it in 96 well systems, where you can extract both from PDMS and plasma, and then difference will give you the idea of binding. So this is how does it work. So basically, when you have analytes in PBS, this pink point, you have, of course, more extracted for given concentration. When you have plasma, because of competitive binding, you extract less. And if you look at details, what you'll find out, the equilibration profile is different for PBS, and it depends on how strong binding are analytes. When the analytes are bound stronger, you can see the equilibration time is shorter because more analytes relatively to that necessary to equilibrate in the fiber are available in the boundary layer. Now, understanding this multi-phase equilibrium will allow us also to design a new calibration procedure. So this was what we discovered here is that, of course, desorption rate of the calibrant from the coating is the same as extraction rate of the analytes from the matrix for most of the biological matrices. So we can use it to develop calibration procedure where we don't exactly know convection conditions. So for example, if you analyze the blood in the dog's vein, as I will show you that in a moment. And basically you do it that way, that you put the fiber with the calibrant into the sample, some of the calibrant being released, some of the analytes being extracted. So you find out a number of extracted analytes and remaining calibrant. By knowing that the system is symmetric, that means extraction time profile is symmetric to the dissociation, the desorption rate constant, the desorption profile of the calibrant. So when you add both together, you have one. Yeah, so you can use this principle here because the only unknown is this amount of analytes extracted equilibrium, which we can calibrate based on matrix match calibration of raw blood. And from that, we can calculate the concentration. So the advantage of this calibrant loaded approach is a kinetic approach, so we can stop the extraction at any time. So basically, when you analyze the blood in a dog's vein, you can reach equilibrium, so you don't need to worry about the convection conditions, or you can use the kinetic calibrations. And so when you compare the data, which is very interesting, you can see this is the standard approach: blood draw from live dog and separation of plasma and then protein precipitation data versus equilibrium conditions of SPME and kinetic conditions, short sampling. You can see the absolute concentration received are identical. And it's not only they're identical, also the profile is identical. So this gives us, of course, a lot of encouragement to look further in vivo studies, which we are continuing nowadays. So this brings me to the end of my presentation. And again, what I showed you is how to effectively use the fundamentals to optimize the method and technologies for green sample preparation approaches. And more information you get from my group website. And I also would like to encourage you to attend the XTech. XTech is supposed to be in Alicante, Spain. However, it's going to be online because of the COVID, but next year is going to be in Chile.